Hello, and welcome to this sort of unusual talk. Let me start with the usual way by thanking the organizers for the invitation and giving me the opportunity to talk about this work, which is a joint work with Oleg Budkovsky and Konstantinos Zariadis. So I will start with a sort of lengthy introduction. In fact, I will start with a very well-known result in the context of regularization by noise, which is the following result by Veretennikov, that stochastic differential equations have solutions under very mild assumptions on the drift coefficient. So even if B is just a bounded measurable function, but you have some noise in the equation, which is captured by the assumption that sigma is non-degenerate, and sigma is also assumed to have some regularity, then this equation has a unique strong solution, which is which shows that adding the noise definitely relaxes the assumptions on B. I mean, without the noise, you would need local Lipschitz or something close to that. And so what we are looking at is how to discretize such equations, which is motivated by the fact that this construction of the solution by Veretennikov is not particularly constructive, and it's not so obvious how standard approximation schemes for stochastic differential equations perform. So to be more concrete, I mean, throughout this talk, we will only look at one type of approximation, which is it's basically just the forward Euler method extended to SDEs. So you just freeze the coefficient, and at each time step, you just make a small change according to where you were before. And okay, if you want to write it in differential form and extend it into continuous time in a way that is sort of convenient for the analysis, then you write it like this, where kappa and t is just the last grid point before t, when the grid is uniform with mesh size 1/n. So seems like a very natural question, and indeed this has been looked at like many decades ago, where Deny and Krylov proved that this approximation indeed converges to the solution, which is sort of good news that even though this solution was obtained in a non-standard way, the standard approximation procedure still works fine, in the sense that at least you recover the solution. And the interesting thing is that if you want to make this a bit more quantitative, that you want to have a rate of convergence, then actually in the extent of, well, in the generality of the previous theorem, there is no known rate. So there are certain subcases where there are works and where there are results. So if you really want to keep B as irregular as it was in the previous slide, then the only result that I know of is this recent work with Konstantinos, where we show rate 1/2 in the case where we are only in dimension 1, and the diffusion coefficient is actually just a constant. And the other direction, where there are many more works, is so of course between bounded measurable B and between Lipschitz B, which would be kind of where their analysis becomes pretty standard and well developed. There's a lot of room between the two, and so there are several works where there are some sort of more regularity assumption on B, and obtaining rate of convergence under these additional assumptions. And I should also remark that again, throughout this talk, we will only ever talk about strong convergence. So the works in the case of more regular B is, well, this is a sample of the results, which is very likely incomplete. Apologies for that. I tried to be sort of have at least a representative sample. So there are two types where this, where this range between bounded measurable and Lipschitz is, well, there are assumptions in between them. So one of the type is where the irregularities are sort of separated. So, for example, in dimension 1, you can imagine coefficients which are Lipschitz on, let's say, finitely many intervals, and so you divide the real line into finitely many intervals. On each interval, you are Lipschitz continuous, but between the intervals, you can have some jump discontinuity. In which case the irregularity is really sort of separated and local. The other type of results are where the irregularity is global, so you don't have special points, or you don't have non-special points. You just assume that for example, the drift is in C alpha. In which case, the drawback of most of these works is that the rate deteriorates as alpha goes to 0. So, exception for this is the last two works with italic, where there are sort of the irregularities are allowed to be, I mean, there are no special points, and the rate is always at least 1/2, let's say. But I don't actually want to continue with this last two and discuss where can they be further improved. Rather, I want to focus on the common method of all of this, where so all of them are in some way or another based on ideas going back to Zonkin and Vertennikov, which is sort of often referred to as the PD method, which relies on the fact that often you can find a transformation phi such that phi of x solves an SDE with a regular drift. Often, actually, you can just find the phi where the new equation has the drift 0. And to find such a phi, you will often have to solve a PD, or at least analyze the solution of a PD. But this has some drawbacks because there are many situations where you don't have Ito's formula. So what we do in this work with Oleg and Konstantinos is take a different toolbox from this regularization by noise literature, which is called suing method or suing lemma, which really goes back to Young integration, but in this context was developed by Kupinelli, and recently a very nice development was, a very nice variant was found by Lem, which is also very useful for our purpose, where there is no Ito formula. So this immediately opens up the door to treat equations with fractional driving noise, or also other situations where you would be in a Markovian setting, so you would have some PD, but the PD would be very complicated, which would be the setting of infinite dimensional noise, for example. Think of SPDs with irregular drift. But I would also like to mention that this approach also offers some improvements in the classical setting where PD approach does apply, and I will be more precise about that later. So the brief outline of the strategy, which is, well, there's nothing too surprising at this point. So consider the additive noise case, where if you compare the two x and xn, then the noise terms cancel, and you can decompose the difference like so. And one thing that you can immediately do is just introduce a notation. At this point, this is only just a notation, but of course I want to be sort of suggestive with this. So I replace the xn by this b tilde. keeping in mind that B tilde is a Brownian motion under another measure. And then what you see is sort of similar type of objects. So, for example, the first object is, you see an average of a Brownian motion. So an average of an irregular function along a Brownian motion, and an approximation of this quantity. And the second is sort of similar, that you have, okay, the same average, and the same average under some perturbation of this this Brownian motion. So let's call this I1 and I2. And yeah, this is what I said, that B tilde is just Xn. It's another notation, but keeping in mind that this is just a Brownian motion after some Girsanov transformation. And well, with both terms, you can do something if you have at least some Hölder continuity from your coefficient. So the first term you can just bound it by n to the minus alpha over 2. So this is kind of trivial. And similarly, the second guy can be bounded by x minus xn to the alpha, and I'm not precise with the norms and the topologies, and I don't intend to be. So the first one would not be a complete disaster because, well, it still gives you some rates. But the second term is quite disastrous because, well, this is the term that you would want to treat with some Gromwell lemma or something, and then the only acceptable exponent is 1. So this is what we want. We actually want to improve both of them, and actually I will only describe a little bit the first one. So improve the rate of the I1 and get the exponent 1 in I2. But as I said, I will only talk about the first one. So just slightly different notation. I now use F for the drift coefficient, F instead of the B from the previous slide. And in fact, I only assume F to be in L infinity. So in this sense, in this case, it's not even clear what is that you have any kind of rate of convergence of this quantity. Actually, L infinity should be replaced by just bounded measurables. You don't want to deal with versions. Okay, so how to bound this quantity, which I now denote E1, thinking the 1 now as a process. So you can think of the upper variable running. And I want to bound the moments of A1, but first I will do something much, much weaker, which is just bind the expectation. So now there is no absolute value inside, I just bound the expectation. This it's not clear why this is helpful, but let me just show that at least we can do this. And this is kind of simple because you just write the expectation of some function of a normal random variable is just the heat kernel applied to that function evaluated at 0. With the normal variable is centered. And the same you can do it for the second guy. And now you have difference of heat kernels at different times, which you can bound basically with any rate up to 1, right? And the price that you pay is that you have a blow up in the, let's say, smaller of the 2 times, which is this blow up of kns to the minus delta. But since we cut off some part of the integral, you can think of this kns as essentially just being s. And then s to the minus delta is gives a perfectly finite integral if delta is smaller than 1. So at least the expectation of A1 is bounded by n to the minus delta. And now the nice thing is that essentially the same argument gives the following bounds that if you bound increments of this process, still all the absolute value is outside, I'd like to emphasize, but you take increments of this process and conditional condition on the initial the smaller time, then you get bounds of this form. So you have some power of n and some power of t minus s. The t minus s. So this comes from the fact that if you integrate something s to the minus delta from, let's say, 0 to t, you would get a t to the 1 minus delta, and in this setting you get a t minus s to the 1 minus delta. And here is where the stochastic Swing lemma can be applied. In fact, this is sort of maybe the simplest version of it, which says that if you have a process, an adapted process, and you can bound its increments in such a way, and so with some constant and with some power of the time differences, and the power of the time differences is bigger than 1/2, then the same bounds you get for the moments of the differences. So this is how you bring in the absolute value. The only thing that you have to keep in mind is that this 1 minus delta has to be bigger than 1/2, which means that delta will be basically 1/2. So you basically get an order of convergence of 1/2. Okay, so just to go back a little bit, so we get a rate of convergence 1/2 of this guy without having any assumptions on the regularity of f, and this is in any LP. So in particular, this is again true for also almost surely. Okay, so I'm a bit late to start talking about the results, but okay, I'll try to be quick. So the first application where we carry out this strategy is the case of fractional driving noise. So SD is driven by fractional Brownian motion, just in an additive way, in which case, of course, this is kind of, there were no previous results as far as we know, which is not surprising given that all of the previous results relied on this PD transformation, which clearly doesn't work for fractional Brownian motion. And so one thing that one knows from the well-posedness theory of such equations is that to have well-posedness, you need alpha to be bigger than 1 minus 1/2h. So you have some regularity criterion for alpha. For example, if h is very large, you have to be close to 1/2 order continuous. And then there's another natural assumption, which is that to make sense of the Euler-Maruyama scheme, you need, well, you don't want distributional B, right? Because then it's not clear what you could consider different approximations, but if you really want to talk about Euler-Maruyama, then you need evaluations of the drift. So for us, by the way, this is a non-trivial remark that, or well, trivial remark, but important remark, that C0 for us is just bounded measurable functions. C1 is Lipschitz continuous functions, and so on. So this is sort of corresponds to the fact that the extension of further scale to integer values is not always, so it's a bit ambiguous, and this is how we choose. So when I say alpha is 0, then B doesn't have to be continuous, just bounded measurable. So under these two kind of minimal assumptions that alpha is non-negative and guarantees the well-posedness of the equation, we have rate of convergence. And okay, so let me go through this estimate. So first of all, the type of error that we bound is not just pointwise. In fact, not even just uniform, not even only uniform between the two paths of the solution and the approximation, but this difference is bounded in C1/2 plus, so slightly better than 1/2 order continuous. In omega, we can choose any LP, so we have any bounds for any moments, which in particular implies almost short convergence as usual. And the rate that we get is this 1/2 plus alpha h. So, okay, of course, you have to modify it a little bit because you cannot go above 1. And you also lose some arbitrarily small epsilon. Okay, so one thing I want to quickly remark is that actually this is even interesting in a relatively regular and actually even in the Lipschitz continuous case and Brownian case. So this is a very particular case. So h is 1/2 is standard Brownian. So for any alpha between 0 and 1, strictly bigger than 0, you get the rate 1 plus alpha over 2. On the other hand, if you look at the like classical proofs of error analysis of Euler scheme, then if you have Lipschitz B, then you get rate 1/2. And if you want more, remember we are in the additive case, so you can in principle get a better rate up to 1. So if you want to get this 1 plus alpha over 2 rate, then you have to require BNC 1 plus alpha. So in this sense, what we prove is, in fact, even gives new results in the regular drift case. But of course, we assume non-degeneracy. Well, in this case, it's the noise is just additive. And I put an asterisk here because I had private conversations, and even so it's written down where it is claimed that B in C1 is enough to get rate 1, but I have never seen a complete proof of this. So if you know anything about this, then please let me know. I would think that the noise and the regularization effect of the noise really has to be used to get this rate 1 for B in C1. Let me go on the next application of the method, of the Sewing method that we have, which is in a context where PD results via PD methods exist, but this is where Sewing method can improve what has been done before. So this is now just standard Brownian noise, but multiplicative. Of course, the noise is non-degenerate, and then this reasonably regular. Only the drift is irregular with some alpha bigger 0 actually. And the rate that is known from the literature is at least half over 2, which is related to what I mentioned at the beginning. But we also know that the rate is at most 1/2 because, well, even in the case of smooth coefficients, it will be this will be the case. So what we can show is that, as a matter of fact, no matter what alpha is, you get the optimal rate. Okay, and again, the convergence is taken in this relatively strong topology. Now, not slightly above, but slightly below the 1/2 norm of the difference of the two solutions, and again, any moments. So let me mention one aspect of the proof which is maybe interesting on its own, which is that you remember in this example we had to look at these approximation problems that you have some process that it was just a Brownian motion. You have the average of an irregular function of some process, and its natural approximation. So and you remember that we arrived to this problem after a Girsanov, so the drift is already removed from the process here. So in this case, the B is not present in X, but the irregularity of the B is captured by the fact that we are looking at F in C alpha, so kind of irregular F. But you remember that we arrived to rewriting it with heat kernels, and we needed appropriate heat kernel estimates. And it turns out that what appropriate heat kernel estimates would be were not really available. So these were studied. These are maybe the oldest references that we found on sort of heat kernel type estimates for the Euler scheme, which is really just a transition bounds for the transition densities of the Euler scheme. But what they had was not really appropriate in the sense that the type of heat kernel estimate we need really has to capture some smoothing. So this is sort of a standard heat kernel estimate, apart from the last term, in the sense that you see that you have a derivative of G on the left-hand side, but only the L infinity norm of G on the right-hand side. And of course, you have to pay a price then, that t equals 0, you will have a singularity. And the singularity has to have the optimal exponent. So it is kind of well known that the optimal exponent here is 1/2, minus 1/2. And to capture both of these phenomena, none of these works are applicable. So this is sort of a key bound that we needed for the proof, proof of basically estimating this guy. So let me conclude by pointing at a few possible future directions. Partially, this is actually already work in progress, because it seems that this approach is applicable in many different directions. So one is that I already mentioned, that when you want to look at SPDs, where again this trick with the Ito formula doesn't really work, because you would get the infinite quadratic variation. So of course, I'm talking about SPDs with space-time noise and with the regular drifter. Other direction would be to go to other schemes rather than the Euler-Mortimer scheme, look at Milstein scheme, etc. So yet another would be to look at B drift coefficient with measured in different regularity scale, which would have the advantage that, of course, Hölder scale will. So you saw that in the, let's say, the standard Brownian case, we always needed some positive regularity, which in particular excluded these examples of piecewise nice functions. But if you look at other scales, in Sobolev scales, for example, then positive regularity can cover this type of drift. Also, it would be interesting to see what happens with Levy noise. So these last three examples have works with the PD approach already, but probably the Swing approach would also give some interesting results. And plus another thing that would be interesting to discover is how this interplays with weak convergence analysis, and maybe there will be other applications as well. Okay, so that was all. Thank you very much for the attention. Here's the link to the paper and archive. And I suppose see you at the discussion on Thursday, if I remember correctly. Thank you.